The wind energy sector has witnessed remarkable advancements in turbine technology as renewable energy gains popularity. These innovations are making wind power more accessible globally. If you're new here, consider subscribing for more videos on energy and power. Bladeless wind turbines represent a new type of turbine without moving blades. Instead, they utilize vortexes to generate electricity. These turbines consist of a vertical mast anchored to the ground, featuring fins that create vortices when the wind passes by. The resulting vibrations in the mast generate electricity. Bladeless turbines offer several advantages over traditional ones, such as reduced noise, increased bird safety, and a lesser visual impact. Moreover, they are more efficient at low wind speeds, making them suitable for urban areas. However, bladeless turbines are less efficient than traditional turbines at high wind speeds and are currently costlier to manufacture. Nonetheless, they hold tremendous potential for revolutionizing the wind energy industry, with expected improvements in efficiency and cost as the technology matures. Floating wind turbines are offshore turbines mounted on floating structures, enabling electricity generation in water depths where fixed foundation turbines are impractical. These turbines open up new areas for offshore wind farms, particularly in regions with limited shallow waters like Japan, France, and the U.S. West Coast. Additionally, locating wind farms further offshore reduces visual pollution, provides better accommodation for fishing and shipping lanes, and captures stronger and more consistent winds. Floating turbines operate similarly to traditional turbines, with wind pushing the blades, resulting in rotor rotation that drives electricity generation. The floating structure ensures stability in rough seas. Different designs exist, including spar-buoy, semi-submersible, and tension leg platforms. While still a relatively new technology, floating wind turbines are gaining popularity, as exemplified by the world's first commercial-scale floating wind farm, Hywind Scotland, capable of powering 20,000 homes. Although currently more expensive than fixed foundation turbines, cost reductions are anticipated as the technology matures. Floating wind turbines offer significant potential for clean, renewable energy production and play a vital role in the future of offshore wind power. AI is increasingly employed in the wind energy sector to enhance turbine efficiency and reliability. Its applications include predictive maintenance, optimal turbine placement, wind forecasting, fault detection, and cybersecurity. Predictive maintenance leverages historical and real-time sensor data, enabling the prediction of maintenance requirements and mitigating unplanned downtime. Optimal placement algorithms optimize turbine positioning based on factors such as wind speed, terrain, and existing infrastructure to maximize wind farm output. Wind forecasting powered by AI facilitates efficient operation of wind farms by predicting wind speeds and directions. AI-based fault detection enables proactive identification of turbine faults, minimizing repair costs and downtime. Cybersecurity measures employing AI safeguard wind farms against cyber attacks. Although AI is still relatively new in the wind energy sector, it is rapidly gaining adoption. As the technology matures, more innovative AI applications are expected to emerge, contributing to enhanced efficiency, reliability, and security in wind energy generation. 3D printing, also known as additive manufacturing, is revolutionizing the wind technology industry by offering new possibilities for designing and manufacturing components used in wind turbines. This innovative technology has several applications and benefits within the field. One of the significant applications of 3D printing in wind technology is the manufacturing of wind turbine components. It allows for the production of complex geometries and customized designs that were previously challenging to achieve with traditional manufacturing methods. For example, 3D printing can create lighter and stronger turbine blades, resulting in increased efficiency and reduced material usage. Moreover, 3D printing enables the production of components on demand, reducing lead times and inventory costs. This flexibility in manufacturing can also facilitate the development of prototype design, allowing for rapid iteration and optimization of wind turbine components. In addition to component manufacturing, 3D printing is employed for the repair and maintenance of wind turbine parts. Damaged components can be repaired by 3D printing replacement parts or reinforcing damaged sections, extending the lifespan of wind turbines and minimizing downtime. By leveraging 3D printing technology, wind technology can benefit from increased design flexibility, reduced manufacturing costs, and improved performance. As the technology continues to advance, we can expect further advancements in the application of 3D printing, leading to more efficient and sustainable wind turbines. Smart grid integration. Smart grid integration plays a crucial role in optimizing the integration of wind technology into the electrical grid. It involves the use of advanced technologies and strategies to manage the variability and unpredictability of wind energy, ensuring its efficient, reliable, and sustainable integration. One key aspect of smart grid integration is demand response, where utilities incentivize consumers to adjust their electricity usage during peak demand periods. thereby balancing the grid and reducing the need for costly peaker plants. Additionally, frequency regulation techniques are employed to maintain the grid frequency within a narrow range by adjusting the output of wind turbines. Energy storage technologies are another vital component of smart grid integration in wind technology. By storing excess electricity generated by wind turbines during periods of low demand, energy can be made available during high demand periods, effectively balancing the grid and reducing the reliance on peaker plants. Internet of Things sensors also play a significant role in smart grid integration. These sensors monitor the performance of wind turbines and the grid, providing valuable data for optimizing turbine operation and grid management. By incorporating smart grid integration techniques, wind technology can achieve increased efficiency, reduced costs, and improved reliability. It enables a more seamless and reliable integration of wind energy into the grid, contributing to the growth and sustainability of renewable energy sources.